Hello, welcome all to the online class on phase transition. So this class is mainly prepared according to the syllabus of the second semester MSc Physics of CMS College Kottayam, and I have used the book by Bowley and Sanchez, Introductory Statistic in Mechanics, for reference. So what are phase? What is a phase? So we know different states of matter. And the well familiar example is water. Water is having different states of matter. Gas when cooled will get liquid, which when further cooled will get solid, superfluid. So these states of matter, different states of matter of liquid, of water, are called phases. They are different phases. Similarly, if you consider a magnetic material, there are paramagnet and ferromagnetic material. They change their magnetic properties at Curie temperature, and these ferromagnetic and paramagnetic materials are different phases. Similarly, we know a superconducting material. So the ordinary material and superconducting material, they change their properties at critical temperature, and this ordinary temperature and superconducting, they are two different phases. So these are the classical examples of different phases, the different states of matter of liquid, of water, paramagnetic, ferromagnetic materials, ordinary material, and superconducting material. They are different phases. So how do we define a phase? A phase is defined as a state of matter having uniform chemical composition and uniform physical state. Physical state means they are having same physical macroscopic physical properties such that density, conductivity, etc. uniform throughout the state. So what does the uniformity mean? Uniformity means we take a representative sample from a solid, and if it is same as any other representative sample, we say that it is uniform. We take two representative samples randomly, and if they are same, we can say that it is uniform. But the challenge to uniformity is uh, the fluctuation. The number of fluctuation or the amount of fluctuation is proportional to n raised to half or root n if n is the total number of particles. Say if we have 20 particles, then the size of fluctuation will be 5, which is very high. There is a little chance of getting a uniform material there. So, but if there are 10 raised to 20 particles, then the size of fluctuation is 10 raised to 10, which is very small. So there will be a meaningful uniformity. So the size of sample must be macroscopic to minimize the effect of fluctuation. So if the fluctuation is infinite or if fluctuation is very large, then there is no meaning to say about uniformity. Okay, so our phase is having uniform chemical composition and uniform physical properties throughout the material. So now what is a phase transition? It is a transformation of the thermodynamic system from one phase to another or one state of matter to another. So transformation of a thermodynamic system from one phase to another or one state of matter to another is called a phase transition. So now we will discuss about different important features of phase transition. When do we say that there is a phase transition? First and foremost important property of phase transition is there will be an abrupt change in one of the properties of the system. One of the properties of the system. So, for example, if we change from ordinary material to superconducting material, we know there will be a sharp change in the electric resistivity. One is having a resistivity, and at critical temperature, it is having zero resistance. So, resistance is having a sharp jump or a sudden change. Also, similarly, liquid have the ability to flow. Once it transforms into a solid, it loses its ability to flow suddenly. Immediately, it is changing its property. Similarly, the magnetic material we discussed, they are all changing different magnetic properties suddenly. So this abrupt change or a discontinuous change is one of the property of phase transition. Second property of phase transition is phase coexistence. So see this figure of a sealed container. and here gas and liquid phases are coexisting inside the container. That means two phases are coexisting in a system. Here two phases of water are coexisting in a container. The third important property is phase separation. See, in the sealed container, there is liquid phase and there is gaseous phase. And there is a meniscus above the water, above the liquid, which separate the gas and liquid phase. So we know in a phase diagram, there is phase boundary lines, boundary line between gas and liquid phase. Similarly, boundary line between solid and liquid phase. So this boundary line separates between two phases. So such a separation or such a distinction will be there for a phase transition. So there will be two different phases and they will be separated. So these are the three important properties of phase transition. I'll say it one again. There will be an abrupt change in one of the properties of the system, phase coexistence, and phase separation. So now we discuss what is a thermodynamic potential. Thermodynamic potential is a function which is minimized subject to all the constraints that are imposed on the system. For a system to attain equilibrium, we know the thermodynamic potential has to be minimized. So we are familiar with this in chapter 5 of the book by Pauli and Sanchez. There we have discussed this in detail. So for a system to be in equilibrium, depending on the conditions of the system, the generalized free energy or generalized Helmholtz free energy or generalized Gibbs free energy will go to minimum. So what are the constraints? So say for example, if we are considering a system which is held at a constant volume and constant temperature or constant pressure, or if the number of particles are conserved, these are all the constraints. So considering all these constraints, if we have a function which goes to minima, such a function is called a thermodynamic potential. To understand it more, we will discuss with the examples of few discuss with the help of few examples. So consider a system held at constant pressure and temperature and having fixed number of particles. So in chapter, if you have any doubt, please refer back to chapter 5. So here the Gibbs free energy has to be minimized to attain equilibrium. We know Gibbs free energy is H minus Ts or U plus PV minus Ts, and the quantities which can change here are energy and volume, because the system is held at constant pressure and temperature. Here pressure, temperature, number of particles are conserved, they cannot change. Here varying particles are energy and volume. When we change the Gibbs free energy with respect to energy, or the first derivative of Gibbs free energy with respect to energy, taking the derivative, we will get as 1 minus Tr by Ta, and if system is in equilibrium, Tr is equal to Ta and the derivative becomes 0, that means G is minimum. Also, we take the derivative with respect to volume, we will get it as Pr minus Tr by Ta into Pa. Since they are in thermal equilibrium, Tr by Ta is 1. So if they are in mechanical equilibrium, Pr is equal to Pa. So if system is in thermal and chemical equilibrium, then dou G by dou V is equal to 0. That means G is minimized. So if system is in equilibrium, thermal equilibrium and mechanical equilibrium, G is minimum. So here G, which is a function of pressure, temperature, number of particles, and which varies with energy and volume, is the thermodynamic potential. So generalized Gibbs, the Gibbs free energy is a thermodynamic potential and it varies as a function of U and V. So we'll see another example. So we consider a system where exchange of particles is allowed. Consider a system at constant volume placed in contact with a reservoir, and exchange of particle and exchange of energy is allowed. And here we know that generalized grand potential phi of G has to be minimized for attaining the equilibrium. So here in this case, phi of G is the thermodynamic potential. And what are the constants here? Here volume, temperature, chemical potential, and other constants, and we can vary number of particles. See, we have used different subscripts. V of A means volume of system A. So system A is having a volume and it is constant. T of R means since our system is in contact with the reservoir, so gradually our system and the reservoir will be having same temperature, and since the reservoir is a heat bath, our system will be having the temperature of the heat bath. Similarly, we are exchanging particles with the reservoir. So eventually the chemical potential of our system and the reservoir will become same. So Tr mu R means system A and reservoir is having same temperature and same chemical potential, and Na means number of particles. So here we understand the subscripts. So Va means V, if we say V only, then we know that volume is for system A. T, if we say T only, then it is understood that Tr and Ta should be same. So now onwards we drop this subscript. So it will be like this only, phi of t, which is a function of, or where v, t and mu are constants, and phi of g varies as a function of n. So after semicolon we write n, that means it varies as a function of n. Is it clear? So another example, consider a system which is magnetic and held in a constant external magnetic field H. Here the generalized magnetic free energy f of h has to be minimized to attain equilibrium. So what is the quantity which can be varied? It is magnetization M. So here magnetization M can be varied so that the thermodynamic potential attains the minimum. F of h, which is a function of external magnetic field, temperature and number of particles, and it varies as a function of magnetization M. So see here, after semicolon we have written M, that means f of h varies as a function of M. Okay. So in all these previous cases, there is a quantity which, at least there is one quantity which can be varied to attain the minimum. In first case, we have two. That means energy and volume can be varied. In the second case, we can vary the number of particles. In the third case, we can vary the magnetization. And if there is no such a quantity, or if a quantity cannot be varied to attain equilibrium, say for example, if in the second case, if number of particles is fixed, or if there is a conservation law, then we cannot change the number of particles. Then how do the system attain equilibrium? Say for example, consider a system held at constant temperature in a constant volume and it cannot exchange particles. Here the generalized Helmholtz free energy has to be minimized. But how? So this is a very interesting problem. This leads to the discussion of phase separation, which we will do it in part 2. So if there is no such a quantity which can be varied to attain the minimum, then it will lead to phase separation and such complications, and we'll discuss it in part 2. So this is all about thermodynamic potential. So thermodynamic potential is a function which has to be minimized subject to different constraints imposed on the system. So we have seen 4 examples also. So next we are going to do an approximation. So what's an approximation? So before that, all the thermodynamic potential can be described by a simple mathematical function, phi, capital Phi, which is a function of small phi. What does that mean? Capital Phi is a thermodynamic potential and small phi is a quantity which can be varied. For example, in the case of a magnetic field, f of h is the thermodynamic potential and m is the magnetization which can be varied. So the approximation is the thermodynamic potential depends only on the average value of phi and is independent of the fluctuations. I'll say it once again. The thermodynamic potential phi depends only on the average value of the parameter which can be changed, and it is independent of the fluctuations in that parameter. For example, the generalized magnetic field f of h depends only on the average value of magnetization m, and it is independent of the fluctuations in m. So that is the approximation. So what is the consequence of this approximation? See, consider if a potential has a single minimum. So here thermodynamic potential has a single minimum here, and the system reaches equilibrium by varying the parameter phi until the system has reached the minimum of phi. So system will vary the phi until it reaches the minimum. So this is the consequence of this approximation. So it will vary the parameter until it reaches the minimum. So consider a more complex case if there are two minimum. So in this case, this is one minimum and this is another minimum. So here this is the lower minimum. This minimum is having lower energy. This one is not having lower energy. But for a local minima, this is a local minima, and sorry, this is a local minima, and this one is the absolute minima. So if a system is in this state, we can say that this is a metastable state, and eventually the system will go to the lower energy state. But there is an interesting development. See, if we increase the temperature, what happens? This was the absolute minima or the lower energy. But as the temperature increases, what happened? It turned to be a metastable state, and the otherwise metastable state now become the lower energy state. So consider this as a case. So if this is a liquid phase, this will correspond to a liquid phase, and this will correspond to a gaseous phase. So liquid phase is having the lower energy, lower potential, and when the temperature increases, what happens? The gaseous phase attains the lower free energy. So gaseous phase is more probable, and the material will change from liquid phase to gaseous phase. Got it? So now we'll discuss about the classification of phase transitions. So this is a very general classification. I don't want you to study this, but just for your understanding, I have mentioned it here. There are two types of classifications: thermodynamic classification. It was done by Ehrenfest, and mechanistic classification. In Ehrenfest classification, it's like first order, second order, lambda transition. First order means the first derivative of thermodynamic potential is discontinuous, then it is called a first order. If the second derivative of the thermodynamic potential is discontinuous, then it is called a second order phase transition. Lambda transition is seen in condensed matter physics and all. So in mechanistic classification, it is like reconstructive displacive order displacement term. So Ehrenfest classification was useful, but it does not take into account the case where a derivative of free energy diverges. So the Ehrenfest classification was abandoned. It's no more used. In the modern classification, we have only these two. The modern thermodynamic classification is like this. We have a first order phase transition and a continuous phase transition. What's a first order phase transition? We already know what is a thermodynamic potential. If the first derivative of the thermodynamic potential is discontinuous, if the first derivative of thermodynamic potential is discontinuous, then it is called a first order phase transition. And if all the first derivatives are continuous, we cannot see a discontinuity in any of the first order derivatives, then such a phase transition is called a continuous phase transition. And obviously, the second order derivative of the third or the fourth order derivative will be discontinuous. But for the time being, if all the first order derivatives are continuous, then it is called a first continuous phase transition. And on the other side, if any of the first order derivative is discontinuous, it is called a first order phase transition. Discontinuous. Remember that if any of the first derivative is discontinuous, there is a change, there is a sharp change. Discontinuous means graph goes like this, then it drops suddenly. So there will be a discontinuity. So if there is a sharp change in any of the first order derivative, then it is called a first order phase transition. If all the first order derivatives are continuous, it is called a continuous phase transition. The classical example of first order phase transition is solid to liquid, liquid to gas transition below critical temperature. And example of continuous phase transition is metal superconductor transition and ferromagnetic phase transitions. Okay. So now we are going to discuss about the features of first order phase transition. These are the 5 important features of first order phase transition. So I am not reading it. We will discuss it one by one. So discontinuity in one or more derivative of thermodynamic potential. So if capital phi is a thermodynamic potential and x are the variables, are the parameters, if any of the first order derivative dou phi by dou xi is discontinuous at the transition, then it is a first order phase transition. For example, consider the Gibbs free energy G. G is equal to H minus Ts, U plus PV minus Ts. And if consider a small change in dg, dg, we will get it as minus S dt plus V dP. And the first order derivatives are dou G by dou T at constant volume. That's called S entropy. And dou G by dou P at constant temperature is called volume, molar volume. So what are the first order derivatives in this case? Entropy and volume. If entropy is having a discontinuity, it's called a first order phase transition. Or in vice versa, if you say in the reverse direction, all the first order, in case of first order phase transition, entropy will be discontinuous. Also, molar volume will be discontinuous at first order phase transition. That means entropy will be having an abrupt change. So that's the first important feature of first order phase transition. What's it? There is a discontinuous change in discontinuity in one or more derivative of the thermodynamic potential. Okay. The second feature is the presence of latent heat. So consider this diagram. So initially well 2 is having the lower minimum and well 1 is a metastable state. As we increase the temperature, the system evolves such that well 1 become the stable state and well 2 become the metastable state. If a system evolves in such a manner, we can say that it describes a first order phase transition. If the minimum states change like this, then we can say that it describes a first order phase transition. The two minima, phi 1 and phi 2. Phi 1 here, this is, say, if this is phi 1, this is phi 1, and this is phi 2, and they vary with temperature at different rates. So entropy at well 1, that's S1 is equal to dou phi 1 by dou T, and entropy at well 2 is S2 is equal to dou phi 2 by dou T, are different. So when system changes from one state to another, there is a difference in the entropy, and this leads to gives rise to a latent heat L12, which is given as Tp into S1 minus St, where Tp is the transition temperature. So are you familiar with this phase transition in day-to-day life? Means, have you seen this latent heat? See, consider we boil a liquid. So we are boiling a liquid. What happens? Initially at low temperature, liquid phase is the most preferable state, or the system state in, or the water stays in the liquid phase. As the temperature increases, what happens? Entropy becomes more significant, entropy increases, and there is a transition from the liquid to gaseous phase. So what happens? The difference in free energy between liquid phase and gas phase becomes smaller, and it reaches a temperature where the free energy of liquid and gas becomes equal. So these two phases are now having equal probabilities. So at that stage, liquid does not convert to gas. So it still needs some more energy. So gaseous phase is having higher energy than liquid phase. So we have to add, so now the free energies are equal, but we have to add some more energy. So we have to supply some more heat, and what happens at this time? Temperature won't change. Temperature remains constant while this heat goes from converting the water from liquid to gaseous form. So the liquid form, so the gaseous form. So at this stage, what we are discussing. So at this stage, the temperature remains constant, but the heat is absorbed to change from liquid to gaseous phase. So this amount of energy supplied at this time and the energy difference between the two phases is called the latent heat. So it is the amount of extra heat you must add to the system to convert from one phase to the another. This heat does not contribute to change in temperature. So once we have a latent heat, once there is a presence of latent heat, we can say that there is a first order phase transition. The presence of latent heat is a significant feature of first order phase transition. Okay. So third important property of phase transition is there will be well-defined boundaries between the phases. So this is the diagram, phase diagram of water. See, consider this line. So this is the boundary. So this is the boundary between solid phase and liquid phase. So these two regions phases are stable and there is a boundary between these regions. Consider here liquid phase and gaseous phase. There is a boundary line separating between the liquid phase and gaseous phase. When the system crosses this line, there is a first order phase transition with a discontinuous change in one of the derivatives of the thermodynamic potential. So this point is called critical point. Do you have any idea what is this critical point? Why this line goes on? If we increase the pressure and temperature, still there will be a boundary line between solid and liquid. But if we increase the pressure and temperature, the boundary line between the liquid phase and gaseous phase stops at a particular point called critical point. Beyond that, there is no phase, liquid phase or gas phase. There is a phase called superfluid, and there will not be any phase transition at this stage. You know what? Because so if we increase the pressure further and further, the liquid cannot get compressed, so its free energy reaches a stage. And if we increase the pressure on gas, what happens? The gas become compressed, their entropy will become minimum, and eventually at one point the free energy of liquid and free energy of gas will become same and the difference will become zero. And since they are not having any difference, there will not be any phase transition, they become one phase, and that phase is called a superfluid phase, which is neither liquid or gas. And this point is called a critical point. Beyond critical point, there is no phase transition from liquid to gaseous state. So whenever we say there is a phase transition from liquid to gaseous phase, we must say that it is below critical temperature. But whatever be the pressure or temperature, there will be a phase transition from solid to liquid phase. You know why? Because uh, so if we increase the pressure and temperature, difference in free energy becomes minimum, but still there will be a difference. You know why? Because solid is having a symmetry. We studied about different symmetries in group theory. So any solid will have a symmetry, square or rectangle or square or triangle or anything, it is having a symmetry. So we have to break the symmetry to make it to a liquid. So that energy, that change will be there. Whenever there is a symmetry, difference in symmetry, there will be a phase separation. So, but in this case, liquid and gas, they both don't have any symmetry. They are in same symmetry state with no symmetry. So there will be no change in symmetry between liquid and gas. But in solid and liquid, there is change in symmetry level. Solid is having symmetry, liquid is not having symmetry. So that change always preserves a boundary line between solid and liquid waste. You can read that further in a website by Stanford is there. They have explained it well. So another important property is of first order phase transition is metastability. So we have already seen this diagram. So here well 2 is the lower energy state and well 1 is the metastable state. As the system evolves, what happens? System 1 becomes a metastable state and system 2 becomes the well 1 becomes a stable state and well 2 becomes a metastable state. I'll say once again, initially well 2 is a stable state and well 1 corresponded to the metastable state. But as the temperature is increased, what happened? Well 1 became the stable state and well 2 changed to metastable state. Consider a particle which was in well 2 and they were happy that they are in the stable state. But as the temperature increases, what happened? Well 1 became the stable state and well 2 is now the metastable state. But the particle has to go to the stable state from metastable state. But there is a potential barrier which does not allow the system from particle from going from metastable to stable state. So what happens here, sometimes the particle stays for so long that they seem to be a stable state, but when the temperature is increased or by thermal activation we decrease the energy barrier and the particle can go from metastable to um, stable state. So super cooled liquid or super cooled water vapor. So one interesting example in this case is when the water vapors are condensed in cloud, they condense to form liquid and their temperature decrease, uh, and even below the condensation point or even below the point where it becomes liquid, its temperature goes beyond that, but still it will be in the water vapor phase. That means they are in the metastable state. What is the metastable state there? The gaseous phase or the water vapor phase is a metastable state there, and it the temperature decreased, but the activation function is, sorry, the barrier is there. So the water vapors cannot go to liquid phase. They remain in liquid phase, but still their temperature is below the temperature required to form liquid. So there a seeding or a nucleating site is needed. If such a nucleating site is given, it will immediately jump to liquid phase. So that is what is done in cloud seeding. So in cloud seeding, they are giving an external nucleating site, and all the water vapors will change to liquid and it will come down as well. So metastability is a property of first order phase transition. And the last property of phase transition is hysteresis. So consider a supercooled liquid. So we lowered the temperature and liquid going from liquid phase to solid phase. So we supercooled it, and what happened? It became solid, but at a temperature which is lower than the melting point. At the melting point, it is not a solid. It was in the metastable state itself. The temperature has gone down. At some further temperature, it becomes a solid phase. So, or think it this way: consider a cycle. We first heat it and then we cool it. We first heat it, we cross a transition temperature and go to the liquid phase, and then we cool it back. It becomes solid at a different temperature. Or considering a particular temperature, the system will either be in a solid state or a super cooled state. So there is a lag. So there is a lag between the cooling, sorry, the heating and cooling. There is a lag between them, and this lag is called a hysteresis. So hysteresis is another property of first order phase transition. So this much we have covered in part 1. In part 2, we will discuss about Clausius-Clapeyron equation and the phase separations. Thank you.